div A is equal to rho. Rho is a function, a number. A is a vector. So remember what we said before, a vector has three components. Div A just gives you a number. How can we reconstruct what A is just given that number? We have the tidal accelerations, which are, in the Newtonian case of three-dimensional space, is just 9. They're specified by the 3 gravitational acceleration things, right? Which are specified, which have to be specified by something else, because we have div A is equal to rho. Rho is a function, a number. A is a vector. So remember what we said before, a vector has 3 components. Div A just gives you a number. How can we reconstruct what A is just given that number? Okay, so that's a challenge. Think about that for a minute. Right? Div A is equal to rho. Rho is a function, a number. A is a vector. Divergence destroys the vector, turns it into a number by adding up combinations of things. You don't have information anymore about the individual components, just combinations. There's no way to reconstruct the individual components from that combination. It's lost information. How can we specify A? So you can't specify it from that equation. There must be another equation. Now, what did we say? What is it about A that allows us to do this?
It's radio.
It's radio. Okay. What equation do we have that tells us that, so to speak, that expresses that in terms of gravity?
Gm over r squared.
Okay, so when in that equation, Newton's equation, he stuck in r hat, so to speak, and that just tells us. But in our differential equation, which is div A is equal to rho, we don't have that. Of course, we can take A as only radial, stick it in there, and then we just get that r squared A prime, etc. Very simple. And we have a number. But where is the equation that says that we can do that? Right, so basically what we need is something like a field equation that tells us this about A. And the answer is, it's the fact that A is the gradient of a potential. Physically speaking, we had the tidal acceleration related to the gravitational acceleration, which is then going to be related to something else physical. And this has to do with what I said about the structure. Okay? We could write the tidal acceleration equation only because it has structure. We write it in terms of the gravitational acceleration.
Mm-hmm.
So there are many, many tidal terms because let's say it's a 3x3 tensor, so it has 9 components, but it can be written, all of those 9 components can be written in terms of the 3 components of the acceleration. So just given 3 things, you can know all 9 things. So the structure that's hidden, that substructure, allows it to be expressed in fewer field equations than you might otherwise think. You don't need 9 field equations for these 9 components of this 3x3 tensor thing. You only need to know 3 numbers because all 9 can be specified by the 3 things of A. It's A prime and A over R and so on. So all you need to know is the 3 components of A and you got it all. But even that is not enough because we only have one thing on the right-hand side, rho. So clearly these 3 components of A have a substructure, that there's one thing, that if you give that one thing, you can find all 3. So that's the progression. There's one thing, which we don't know yet what it is, which if you specify that, you can find all 3 components of the vector, A. Given those 3 components of the vector, you can find all 9 components of the tensor tidal acceleration.